Okay, so I think quiz 2 due in, I guess, 7 hours. And quiz 3, it's due by Friday, I think 11:59 p.m. So this is a single attempt, yeah. So this one, single attempt, and it's like 15-20 minutes. So it's only multiple choice or true false. Yeah, so it shouldn't be too hard. And it's like math 2B questions. So, okay. Any questions about the quiz?
Just wondering about how many questions are there?
I think for quiz 3, right?
Yeah.
I think there's like 4. It's like 2 multiple choice and 2 true false or something like that.
Okay. All right. Thank you.
Yeah, it's not long. It shouldn't be too hard.
Okay.
So, okay. So, and I think you can see it right now. I think it's on like the quiz tab maybe on the canvas if you could find it. So, okay. So let's go over pointwise and uniform convergence. So pointwise convergence. So Fn goes to F pointwise on S if and only if for all epsilon greater than 0 and x in S there exists n such that for n greater than or equal to n, Fn of x minus f of x is less than epsilon. So here, n depends on epsilon and s, right? So if my x changes, my n could possibly change. So what uniform means, kind of like how you have uniform continuity versus continuity. So we have Fn goes to F uniformly if and only if, the same thing as uniform continuity, right? It doesn't depend on your point x. So for all epsilon greater than 0, there exists n such that for n greater than or equal to n, Fn of x minus f of x is less than epsilon for all x and s, yeah? So this n will hold no matter what x is. So I guess let me write on s. Okay, so examples are sequences without x, right? Sequences without x that converge, right? Because, for example, if Fn of x was 1 over n, it's clear that this goes to 0, right? And it's clear this is independent of x because there was no x to begin with. This function just takes any value x to 1 over n. So this is an example of something that converges uniformly, and vice versa, right? A sequence that doesn't depend on n, right? It's clear it's uniform because there's no Fn of x just converges to itself. It's just a sequence of whatever the function of x is. For example, like, right? I mean, this is just the sequence where n is 1 is x squared, n is 2 is x squared, n is 3 is x squared. It's pretty clear that there's no dependence on n, right? So these sequences converge uniformly, clearly. So another example would be Fn of x is 1 over n, let's say cosine of nx, right? So this converges, it's clear it converges to 0 because as n gets big, the denominator grows. But to show it's uniform, well, goes to 0 uniformly. To show it goes to 0, well, you just need to choose n such that 1 over n, so let epsilon be bigger than 0. Choose n such that 1 over n is less than epsilon, then you're done, right? Then for n greater than or equal to n, 1 over n cosine of nx. Cosine's bounded by 1, right? So this is just 1 over n, which is less than or equal to 1 over capital N, because n is bigger than n, which is less than epsilon, right? So note here, the reason it's uniform is because this thing has no x dependence, right? This part will hold no matter what x is. So convergence is uniform. Okay. Now, one important thing is suppose Fn. So this is important. Yeah. So I'll call it star. Suppose Fn is continuous, and Fn goes to F uniformly. Then F is continuous. So this is a nice thing. So I showed in last discussion like a sequence of continuous functions that don't converge to a continuous function, right? So in fact, there exists a sequence of continuous functions that converges to something that is discontinuous everywhere. So you really need this uniform thing, this uniform property, to guarantee like the limit is continuous. Okay, so so that's really the session. So I think the best way to have you all understand this is do questions. So I'll be doing a lot of questions today. So what happened? So let's do 24.1 first, right? So I need to show Fn of x converges to 0 uniformly on R, right? So this is 1 plus 2 cosine squared nx divided by root n. Why do I keep, okay. So 24.1. Note that when you see cosine and stuff, it's somewhat, clear it's like uniform because cosine is bounded by 1, but okay. So what we are going to do is, let me see, let me think. So instead, it suffices, I mean, unless you're okay with there exists an n such that 1 over root n is less than epsilon, let me just say that let me just say so basically I want to show for all epsilon greater than 0 there exists n such that for n greater than or equal to n, Fn of x minus 0 is less than epsilon. So let me just say this is the same as, so this is what? This is just 1 plus 2 cosine squared nx divided by root n is less than epsilon. So I don't really like the square root because I just want to show how Archimedean property works and density of rationals, right? So this, can we all agree that this is the same as showing the square? So 1 plus 2 nx squared over n is less than epsilon squared. Yeah, I mean, to go from one to the other, you square or you square root, right? So okay, now that we have this, so let epsilon be bigger than 0. And if you work this out previously, you'll see that choose n such that 9 over n is less than epsilon squared. So why is this possible, right? There's two ways you could do this. So two ways is I mean, honestly, since there's a 9 there, it's easier to just say by Archimedean property. So for those who forgot, given A bigger than 0, B bigger than 0, so this is bigger, there exists positive n integer, right, such that n times A is bigger than B. So how am I using this? I am using this for A equals epsilon squared and B is 9. So there exists n. So by Archimedean property, there exists n such that n times A, which is epsilon squared, is bigger than 9. And then when you divide up by n, you get that, right? So you get this thing. So one way is to use Archimedean property. And I guess if you, another way would be to use, say, density of rationals. But okay, but let's see why I chose that, right? So if you work this out, if you square this, you will get, if you square this term, you will get 1 plus 4 cosine squared nx plus 4 cosine to the 4th nx over n. And so let's say, so choose n such that that's true. So for n greater than or equal to n, we have this. So we could use triangle inequality, right? This is less than 1 over n plus 4 cosine squared nx over n plus 4 cosine to the 4th nx. Sorry, this looks ugly. To the 4th over n. And we could bound cosine squared and cosine to the 4th by 1, right? This is 1 over n plus 4 over n plus 4 over n, right? Which is 9 over n, right? And since 9 over n is, since n is bigger than n right here, right here, from this, this is smaller than or equal to 9 over capital N, and we chose 9 over capital N to be less than epsilon squared, right? So we are done. And note this is uniform because this thing has no x dependence, right? So yeah, so we showed this, right? So yeah, okay. So that's the first example. So let's show something that is, maybe not pointwise. So, okay. So I'll do 24.2. I actually wrote the problem down. So for x in 0 infinity, let's do fn of x is x over n. So let's show this is true first, right? So show at least pointwise it converges, right? So if x is like 1, like this should converge. When x is 2, it should converge. When x is 3, it should converge. And it certainly does, right? For each one, for x in 0 to infinity, it converges to 0, right? No matter what number you choose, like x is 5, 5 over n converges to 0, right? So, I'll let you, show pointwise convergence, right? So let me say this. So let epsilon be bigger than 0. Let x be in 0 infinity. Right? I just need to show it converges at every point. So so basically want to show there exists n such that for n greater than or equal to n, absolute value of x over n is less than epsilon, right? And that's clearly true, right? So choose n. So x over n is less than epsilon. So this is, again, Archimedean property. Then for n greater than or equal to n, we have that x over n is less than or equal to x over capital N, which is less than epsilon. Right? But note that this depends on x, right? So this is pointwise, right? Pointwise convergence, not uniform. At each point I converge. Okay. So now let's go to a uniform continuity, right? So how are we gonna do this? So this is part C. I'm gonna skip part B first. So does Fn of x go to 0 uniformly on 0 infinity, right? So so let's assume it does, right? So let assume it does. So let epsilon be 0. Since we assume it goes to 0 uniformly, there exists n such that for n greater than or equal to n, x over n is less than epsilon for all x in 0 infinity, right? That's what it means to converge uniformly. I could find some capital N such that I'm less than epsilon no matter what x is. But this is false, right? Because if this holds, this has to hold for n bigger than or equal to n. So in particular, it holds for this, right? This has to hold, but this can't happen, right? You choose like x large enough, right? I mean, x goes all the way to infinity, right? This, what's the value of x over n is going to be bigger than epsilon, right? So if you really want it to be pedantic, this is how. Let me just change it. So if we assume it converges uniformly, it has to hold for all epsilon. So let's just choose epsilon as 1. Then there exists n such that this thing is true. Then in particular, it holds for this, right? So here, in this case, you just choose x to be n plus 1. Then x over n is bigger than 1, right? So yeah. So you see, it doesn't converge uniformly on 0 infinity, right? I mean, you just pick a large enough value for x. So now the next question is, does Fn of x go to 0 uniformly on 0, 1? And in this case, I mean, it does, right? So let epsilon be bigger than 0. Choose n. So 1 over n is less than epsilon. Again, Archimedean property. And in this case, since x is in the interval 0, 1, the biggest x can be is 1, right? So this is, sorry, I skipped a step. For n, then for n greater than or equal to n, right? This thing is bounded by 1 over n, right? Because x is in, I mean, the biggest it could be is 1. And this is less than or equal to 1 over n, which is less than epsilon, right? So this, it is yes, so uniform. And I guess, well, why did I write D? Maybe it should have been B because I skipped it. I'm not sure, but so this is uniform, and this one's not uniform, right? Okay. Any questions so far? Okay. Let's go over another example. So let's do 24.6. So yeah, let's do an even number. So x minus 1 over n squared. For what? For x in 0, 1. So well, x minus 1 over n squared. Okay, so A, does this converge pointwise? So what do you all think? Does this sequence converge pointwise? So what happens when n goes to infinity, I guess? So like 1 over n goes to 0, right? So you should expect this. So this converges pointwise to, so goes to x squared pointwise, right? So I mean, hopefully that's clear, right? If you take the limit, the 1 over n becomes 0. So you just have like x minus 0 squared. Okay, so now the second, so I'll let you prove this, right? Let you show this. So good practice on the definition of pointwise convergence. So B does, well, does this converge uniformly on 0, 1, right? Okay, so how are we going to do this? Any ideas? Okay, so let's do this. So let's write it out first, right? So want to show for all epsilon bigger than 0, there exists n such that. So by the way, when I write capital N, it's like a natural number. Yeah, it's not some like irrational thing. So that for n greater than or equal to n, I have fn of x minus f of x, right? So before my f of x, a lot of time it was 0, but in this case it's not. So minus x squared is less than epsilon, right? So let epsilon be bigger than 0. So let's do the scratch work first, right? So in this case, I won't tell you what n is. So let's do the scratch work. So let's FOIL this out, right? So I have x squared minus, I guess, 2x over n, right? 2x over n plus 1 over n squared minus x squared, right? Now, the x squares cancel, and I get, I'll just get rid of the negative. So this is 2x, oh, maybe I won't get rid of negative yet. So, okay, so from here, we could triangle inequality, right? In which case, now I can get rid of the negative sign because absolute value gets rid of negative signs. So, okay. So here, what can I bound this one by? So always pay attention to where your x is, right? See if you could bound it. In this case, it asks, does it converge uniformly on 0, 1? So here you see the biggest this term can be is when x is 1, right? So this is bounded by 2 over n plus 1 over n squared. Okay, so formally, I mean, then you just say this is, for n sufficiently large, this is less than epsilon, right? I mean, 1 over n squared and 2 over n go to 0, right? But let's do this formally, even though it's clear, right? By Archimedean property, there exists. So I'm using it twice, right? Using it twice. Using twice because I need one for like this term and one for this term, right? So there exists n1 such that 2 over n1 is less than epsilon over 2, and there exists n2 such that 1 over n2 squared is less than epsilon over 2. So hopefully you all see what my n is now, right? So I need it to hold for both. I need both of these to hold, right? So I'm going to let n be the maximum, right? So both of these hold. And in this case, for n bigger than or equal to n, right? So yeah, I already let epsilon. So here, right, we did the calculation, right? So we set from here, right, x minus sum x minus 1 over n squared minus x squared. We did all that calculation and said it was less than or equal to 2 over n plus 1 over n squared. Now, since n is bigger than capital N, this is certainly true, right? Now, n was the maximum of n1, n2. So n1 is smaller than big N. I mean, n1 is smaller than n. So this thing is certainly true, right? If I have a smaller denominator, my number's bigger. And same idea here, right? n2 is smaller than n because n is the maximum of the two. So this is certainly true. and we said both of these was less than epsilon over 2, right? So we get epsilon. Yeah, the reason I chose epsilon over 2 was just to get epsilon. But yeah. Okay. So everyone good so far? So let me recall two sequences fn of x, gn of x. Recall that we have the usual thing, right? You all learned this before. So if assume, let me write this. Let me erase this for now. So assume fn of x goes to f of x, gn of x goes to g of x, right? Then we have the usual, the sum, goes to the sum, right? And similarly, the product goes to the product, right? So this is pointwise. So I will leave it to you to show sum goes to sum, but what you're going to see is not true if fn of x goes to f of x uniformly. So these are all pointwise, right? So this is pointwise. So if fn goes to f uniformly, gn of x goes to g of x uniformly. Not the case. Fn of x, gn of x goes to f of x, g of x uniformly. So it is true it goes to it pointwise, right? Because I mean, it's enough here that fn goes to f and gn goes to g pointwise for this to be true. So it's certainly true if fn goes to f uniformly and gn goes to g uniformly. But it's not true that their product goes to whatever uniformly. I mean, a classic example is, so this goes to f of x is x uniformly, right? That is clear because there's no n. Your sequence is just the sequence of x's. And the thing I went over just a while ago, this thing goes to 0 uniformly, right? It's clearly independent of x because there's no x. So, but their product does not go to 0 uniformly on R, right? So recall here, I proved this just above. So let me go up. Right here, right? 24.2, right? So this thing. We showed in part C, does Fn of x go to 0 uniformly on 0 infinity? And the answer was no, right? So here's an example of where we have two things going to something uniformly, but their product doesn't. Okay, is everyone clear so far? Some still holds. Some is nice. So, but product isn't. Okay. So let me conclude with the hardest question of today. So this is actually requires some thinking. So, but this is the proof-based one. So let's do 24.7. Fn is a sequence of continuous functions on AB that converges uniformly to f on AB. So, 4. Fn continuous functions on AB, and Fn goes to f uniformly on AB. Okay, so, let me continue the problem. So show if xn is a sequence in AB and xn goes to x, then this thing goes to f pointwise, right? So show if xn goes to x. So this is clearly just point goes to x on where these two are defined on AB, right? AB. Then limit n goes to infinity. Fn of xn is f of x. Okay, so let's write out what we want to show, right? So want to show for all epsilon bigger than 0, there exists n such that for n greater than or equal to n, this thing is close to this, right? So how are we going to do this? So we using these two, right? And the fact xn goes to x. So something you'll learn very useful in real analysis is you add and subtract the same term. So one idea is, okay, I want to make this small, right? So first off, scratch work. So one thing I can do is I can say, okay, I can subtract f of xn and add f of xn and then minus f of x, right? This and the above terms are equal, right? I just added and subtracted the same term. Now, why is this nice? Because here, can I make this small? I can, right? Because Fn goes to F uniformly, right? So remember, uniformly means it doesn't matter what the point is, right? It could be x1, x2, x3, like the sub n doesn't matter because it's uniform. So your capital N will hold for any x value you choose, right? So I can make this small by can I just write by Fn goes to F uniformly. Now why can I make this small? Well, the idea is what is a property of uniform convergence? The star I wrote, right? So let me go back up really quick. So there was a star. Yeah, right here. A sequence of continuous functions that go to F uniformly. What's the result? F is continuous, right? So right now, we are exactly in this situation, right? Fn is continuous and Fn goes to F uniformly. So we get that F is continuous, right? So if you recall what continuous means, so continuity, what does that mean? It means this, right? Limit n goes to for any sequence. This is true, right? That's, I mean, this is the sequence definition for continuity. But so we can make this small, right? As f is continuous. Okay, is everyone good with the plan of attack here? Yeah? Okay, so let's get started. So we'll need two things. So I'll write it out, and then I'll let you all, figure out why I chose certain stuff. So f is, so let's let epsilon be bigger than 0. So right, I need to show this holds for all epsilon. So let's let epsilon be bigger than 0. Okay, now what does it mean that f is continuous, right? F is continuous on AB. So let me use epsilon. By definition, it means this, right? For all epsilon 1, there exists delta such that if x minus y is less than delta, then f of x minus f of y is less than epsilon, right? So delta here, depends on my x, but right, it's not uniformly continuous. But so what I'm gonna do is I'm gonna let epsilon be. You see here, what I'm gonna do is I'm gonna use triangle inequality, right? So here I'm gonna use triangle inequality. So I need epsilon over 2. So let's let epsilon be epsilon over 2. Then since f is continuous, then there exists delta such that if x minus y is less than delta, what do we get? F of x minus f of y is less than epsilon over 2. Yeah? Okay. So I need this thing to hold, right? I want like my my sort of like my y to be like my x, and my x to be like my xn's, right? So here, what we will do is we will say, okay, sorry, let me just write for fixed point x, right? It's not for any x. If it's for any x, it's uniform continuity, right? So yeah. So remember, let x be in AB. Yeah. So we're not showing a uniform convergence here, right? So when we write this, what we want to, when we write like limit fn xn equals f of x, it means pointwise. So, okay. So for x and AB, this is true. Now so here, this is only true if my points y are close enough to x, right? If it's within the delta interval. So I need here my xn's to be in delta interval, right? So, but we know we are given that xn goes to x. So what does that mean? Xn goes to x means for all epsilon 2 bigger than 0, because I used epsilon 1 already, there exists n1 such that for n bigger than or equal to n1, xn minus x is less than epsilon 2, right? That's what it means for a sequence to converge to x. So this must hold for all epsilon 2. So choose epsilon 2 equal to delta. Then there exists n1 such that for n bigger than or equal to n1, xn minus x is less than delta. So now I'm in that delta interval, right? Now 3. We were working here, right? We need to work on this side too. So 3 is, we have that fn goes to f uniformly, right? So what does that mean? So that means, let me just write it again, for all epsilon 3 bigger than 0, there exists, I used n1, right? n2 such that for n greater than or equal to n2, fn of x minus f of x is less than epsilon 3. And this holds for all x in AB, right? Because it's uniform, right? It's uniform convergence. So this, it doesn't matter what the input here is, as long as they're the same, right? As long as x and x. So here we're gonna let epsilon 3 be our second epsilon over 2. Then there exists n2 such that for n bigger than or equal to n2, fn of x minus f of x is less than epsilon over 2 for all x in AB. Okay, so now we're done. So here, let's bound stuff now, right? So we have fn of xn. Let me just write it all out. Minus f of x is, again, we add the term, right? Fn of xn minus f of xn plus f of xn minus f of x. And then triangle inequality. So again, so choose n to be maximum of n1, n2, right? Then for n bigger than or equal to n. Yeah, this is true, right? So we have this. So this is just triangle inequality. Hopefully nothing, nothing too hard here. So the hard part. So here, so why is this is less than epsilon over 2, right? By 3, right? I have that, it's just this result, right? This result holds for all x in AB. So in particular, it'll hold for any xn. So this is less than epsilon over 2 by 3. And so here, right, by 2, xn minus x is less than delta, right? So let me recall. From 2, I have that xn minus x is less than delta. And then from 1, by 1, if we go back to 1, whenever x minus y is less than delta, f of x minus f of y is less than epsilon over 2. So this thing, I get the result, right? So so this is less than epsilon over 2 plus epsilon over 2, which is epsilon. So this is really hard, but it really forces you to think of the definitions really carefully and use it. So I suggest all of you, close, don't look at the notes and try to do this problem. So it really tests whether you know, like, the definitions well enough. So yeah. Okay. So that's all I have for today. Any questions on anything? Okay. Thank you. There's chat. Make sure you do your quiz.